today, we're going to dive into a really cool engineering challenge. How do you build something that's incredibly strong, but without making it incredibly heavy? We are on a quest for the perfect cylinder, and we're going to see how advanced composite materials are getting ready to replace old-school metal in some of the world's most demanding machines. It's kind of weird when you stop and think about it. We've got self-driving cars, we've got rockets that can land themselves, but a lot of their most important parts are still made of steel. That's a material that's basically been the same for over 100 years. So the real question is, why are our most futuristic machines still lugging around all this old-world weight? Well, to answer that, we've got to first talk about the problem with metal itself. I mean, for generations, it's been the absolute backbone of industry. But for today's high-performance world, its limits are starting to become a real roadblock. And what you need to understand is that these problems are all connected. The sheer weight of steel means you need more energy to move it around, which just kills efficiency. It rusts, it corrodes, that means more maintenance. And over time, it just gets tired. It suffers from fatigue, which means it could fail after a certain number of uses. For industries like aerospace or high-end automotive, where every single gram counts, these aren't just little problems. They're deal breakers. So, if metal is the old, aging champion, who's the new contender, ready to step into the ring? Well, the answer is in the amazing world of advanced composite materials. The specific material we're looking at today is called e-glass/epoxy. The easiest way to picture it is, imagine a super high-tech version of papier-mâché, but instead of soggy paper and glue, you have these incredibly strong glass fibers all suspended in a super tough epoxy resin. When you combine them, you get a material that's way, way stronger than either of its parts alone. And this slide right here, this is why engineers are so excited. Composites aren't just lighter. For this kind of job, they're better in almost every way that matters. They don't rust. They last way longer than metal before getting fatigued, and here's the absolute game changer. Their properties are tailorable. You can literally design the material's internal structure to handle specific stresses from specific directions. You could never, ever do that with a solid chunk of steel. But saying a material is tailorable opens up a huge question. What's the best way to tailor it? To figure that out, engineers decided to put 5 different designs through the ultimate engineering gauntlet, a whole series of tough digital tests designed to crown a single champion. Now, the secret sauce here isn't just the stuff the material is made of. It's the direction the fibers are pointing in each layer. It is all about the layup. A tiny change in a layer's angle can completely change how the final part acts under pressure. So, let's meet our 5 contenders. Each one has 4 layers, but the fiber angles are all different. You've got Contender 1, the unidirectional design, where all the fibers line up in the same direction for maximum strength along that one axis. The others mix it up with angle ply or cross ply layups, using angles like 0, 90, and 45 degrees to get a more balanced, all-around kind of strength. So, which one is going to come out on top? The gauntlet is made of 3 brutal rounds. First, a static pressure test to check its raw stiffness. Second, a modal analysis, which is basically a shake test to see how well it handles vibrations. And finally, a transient analysis, which is a simulation of a real-world moving load to test how it performs in action. All right, the contenders are ready. The tests are set. It is time for the clash of the configurations. Okay, round 1 is all about handling pressure. The engineers pumped a constant pressure inside each cylinder to see, 1, how much it would bend or deform, that's a measure of stiffness, and 2, where all the stress would build up. And whoa, we have a clear winner for pure raw stiffness. The unidirectional 0000 configuration barely even flinched. It showed 52% less deformation than some of the others. With all its fibers lined up with the force, it's an absolute rock. But hold on a second, there's a twist. While that unidirectional design was the stiffest, it also focused all that stress into a few very specific, potentially dangerous points. The real winner for managing stress was the 0, 90, -45, 45 design. Its angled layers did a beautiful job of spreading the load out evenly, which is what you really want for long-term durability. It's a classic engineering trade-off, right? Do you want brute strength or do you want smarts? All right, on to the shake test. So every object has frequency it just loves to vibrate at. Think of a singer hitting just the right note to shatter a wine glass. That's resonance. In a machine, resonance is a disaster. It can literally shake parts to pieces. So for this test, a higher natural frequency is way better. It means the part is more stable. And the winner of the shake test, by just a hair, is the 0090 -3030 configuration. But honestly, what's really important here is that all the composite designs did incredibly well. They all had very high natural frequencies, which tells us that they're all naturally great at resisting vibration. And now, it's time for the grand finale, the test that simulates the real world. This analysis models how the cylinder handles forces that are changing all the time, just like they would inside a car's suspension or a robotic arm. We're looking for stability and control here. And the results were crystal clear. The 0/90/45/45 configuration was the star of the show. It vibrated less, and it was way better at damping, which means absorbing energy. When things got dynamic and unpredictable, it was the most stable and reliable of the whole group. Okay, the gauntlet is over. We saw a specialist that was super stiff, we saw another that was great against vibrations, and we saw a clear winner when things got moving. It's time to tally the scores and finally crown our overall champion. And the optimal design is, drumroll please, the 0/90/-45/45 configuration. It may not have won the first round for raw stiffness, but its amazing ability to distribute stress and its rock-solid performance under moving loads make it the best all-around choice for the real world. And this table shows you exactly why. The unidirectional design, 0000, was kind of a one-trick pony. Excellent at stiffness, but just good elsewhere. Our champion, the 0/90 -45/45, is good to excellent across the entire board. It's the balanced athlete that wins the decathlon, not the specialist who's only good at one event. So, we have our winning design. But what does this really mean for the technology we all use? Well, it points directly toward a much lighter, much higher performance future. Let's just put this into perspective. Compared to the old mild steel it's meant to replace, our winning composite cylinder is an incredible 50 to 70% lighter. It doesn't rust, it lasts longer, and you can tune its properties perfectly for the job. This is a total knockout victory on every single point. And this isn't just some theory in a lab. The implications here are huge. We're talking lighter cars that are more fuel efficient, industrial robots that are faster and more precise, more reliable parts in airplanes, boats, even offshore oil rigs. At the end of the day, less weight and more strength means better performance pretty much everywhere. You know, this whole thing takes us way beyond just building a better cylinder. We've moved from just choosing a material to actually designing a material, layer by microscopic layer. And it really makes you wonder, now that we have this kind of control, what on earth are we going to build next?